We're now going to work on something called proving trigonometric identities. So the idea here is that we're going to be given a statement that says that we have this left side uh, and that it happens to be equal to this right side, even though they don't really look much like each other right off the bat. And it's going to be our job to prove that this left in fact equals the right. Now, when you are proving a trigonometric identity, there are a couple of ways to go about it. So on the one hand, you can start with the left-hand side and do a series of steps where each time you're rewriting the left-hand side in some new way, and then after a while, you end up transforming it into the right-hand side by a series of valid algebraic steps. You could also start with the right-hand side and do the same thing, do a bunch of valid algebraic manipulations until you arrive at the left-hand side. And then the one other thing that you are allowed to do is you can work on the left-hand side, do some algebraic steps to it until it equals some particular thing. We'll call that particular thing square. And then if you can work the right-hand side also and turn it into that same thing, then you've also proved that they're the same, because the only way they can both be equal to the same thing is if they're the same. So those are the three ways you're allowed to prove identities. The one thing you cannot do is start with the statement that's already there and start moving things from side to side. Like you can't subtract tangent of x from both sides, for example. We don't want you to like square both sides or something like that. You don't do that, because in order to start doing algebraic steps to the left and right hand side of an equation, you have to assume ahead of time that that equation is true. So that's the one thing you have to avoid. Now there's a couple of rules of thumb that are helpful here. Usually, here's number one, usually it's easiest to start with the more complicated side. So whichever one kind of has more to work with, essentially. And number two, if you get stuck, it might find it helpful to rewrite all the functions in terms of sines and cosines. All right, so let's try to apply these ideas here. So I have a left, I have a right. I would say the right-hand side is the more complicated of the two. So I'm going to go ahead and start with it. So the right-hand side is equal to the sine of x times the secant of x plus the cotangent of x. All right, so we started with the more complicated side, which was our first kind of rule of thumb. And then the second one, it's often helpful to write everything in terms of sines and cosines. So I can use my definitions to write secant as 1 over the cosine of x, and the cotangent as the cosine of x over the sine of x. And then I distribute through, and I have the sine of x over the cosine of x in the first term, plus the sine of x times the cosine of x over the sine of x in the second term. And then, of course, at that point, I can see that I have sine of x canceling, and we know that the sine over the cosine is the tangent. So this gives us the tangent of x plus the cosine of x. And of course, that is the left-hand side of our original statement. And the moment that we have the right-hand side equaling the left-hand side, we're finished, because we have proved that this statement is true. All right, so let's take a look at a couple other examples here. All right, so in this first one, I think we have a clear candidate for what the more complicated side here is, right? I don't think there's any question in our mind, and this is an equal sign, by the way, equals. There's no question in our mind that the left side is more complicated than the right-hand side. So let's start with that left-hand side. So that's going to be equal to the sine of theta over 1 plus the cosine of theta plus 1 plus the cosine of theta divided by the sine of theta. Now at first this might be a little bit intimidating because you might say, I don't understand how in the world this is the same as the cosecant of theta. And that would be understandable. So the key here is not to try to make the one side into the other all in 1 or 2 steps. At first, just ask yourself, you know, what do I definitely need to do to this side in order to make it more like the right? Well, for one, I can't have 2 terms. The one on the right only has a single term. So I should start thinking about how can I make this into 1 term? And of course, when we're talking about fractions, that's going to mean finding a least common denominator. So I'm going to need to multiply the top and bottom of each of these fractions by the appropriate thing so that I can get a common denominator in order to be able to add these fractions together. So of course, I'm going to multiply the top and bottom of the one on the left by sine, and I'm going to be multiplying the top and bottom of the one on the right by 1 plus cosine. So what we get left with here is sine squared theta in the first term plus 1 plus cosine theta squared. This is 1 plus cosine theta on bottom times the sine of theta. And as I look at this, I'm going to realize that I'm probably going to need to go ahead and multiply this out in order to have any hope of having things cancel, right? I cannot cancel 1 plus cosine theta with the 1 plus cosine theta here because it's being added to everything else. So I'm going to go ahead and FOIL this out. So this is going to be plus 1 for the first, plus cosine theta, 1 times cosine theta, plus cosine theta, and then the last would be plus cosine squared theta. All right. Now, anytime we see within a particular expression our Pythagorean identity showing up, we want to be able to recognize it. So I've got sine squared plus cosine squared, right? And that's the identity that we should definitely have on the tip of our brains at all times. So I'm going to start by just getting those together. Putting the sine squared and cosine squared theta next to each other. Plus 1 plus, and then of course cosine theta plus cosine theta is 2 cosine theta. And that's going to all be over 1 plus cosine theta times the sine of theta. All right. And at first you might wonder if we're really making good progress or not. All right, but this thing turning to 1 really helps us out, right? Because this is going to be 1 plus 1 plus 2 cosine theta all divided by 1 plus cosine theta. And it's always good to kind of peek at the right side, you know. What are we trying to shoot for? 2 cosecant theta, which we know is 2 over sine theta. So what that means is that we're happy, oops, I forgot to write it, we're happy with this sine theta that we have in the bottom. We're not so happy with the 1 plus cosine theta, so we're hoping there's a way to get rid of that. Now, of course, 1 plus 1 gives me 2. So the only way we're going to get this 1 plus cosine theta to go away is if we are able to have 1 plus cosine theta appear up here as a factor. But of course, because of the fact that we have 2 in the numerator of, in both terms of the numerator, I can factor it out. And what am I left with? 1 plus the cosine theta. So my 1 plus cosine thetas go away. This is equal to 2 over sine theta, which is equal to, of course, 2 cosecant theta, which is, at long last, my right-hand side. So this is a good example of a problem where you just kind of have to take it a step at a time and keep the faith, and you're doing little things along the way where you're saying, okay, how can I make it look a little bit more like the other side, a little bit more? And at first our motivation is just simply, hey, I've got 2 terms right now, the right side has only 1 term, so let's work on getting it into a single term. All right, so let's take a look at example 5 here. We want to prove that 1 plus sine t over cosine t is equal to cosine t over 1 minus sine t. Here, the 2 sides are, really, neither one of them is really more complicated than the other, so it doesn't really matter what we start with. So I'm just going to start with the left-hand side here. So the left-hand side is 1 plus sine t over the cosine t. Now here's another one where we want to peek at the right side and just understand that, we're not going to be able to do all this in one step. So let's just make what we know needs to happen. So this, I know I've got to have a 1 minus sine t in the bottom. And so at first I might not have any clue how I'm going to get rid of the cosine, but let's just do what we can. Let's go ahead and make sure that we get 1 minus sine t to appear on the bottom. And of course we can always do that as long as we multiply both the top and the bottom by 1 minus sine t. All right, so on bottom here I've got that. Now ultimately I'm going to want to get rid of cosine. In order for that to happen, the only hope I have is that if I can make cosine cancel with something on top. And right now there are no cosines. So I know that what I'm going to need to do is go ahead and FOIL this out. So I'm going to have 1 times 1 is 1. The outside is minus sine t. The inside is plus sine t. That's interesting. And then we have minus sine squared t. And that is all over cosine t times 1 minus sine t. All right, so of course the negative sine t and the plus sine t, they do go away, right? So what we're left with here is 1 minus sine squared t divided by cosine of t times 1 minus sine t. And we're actually almost done, as long as we recognize one thing. So not only, like in the last problem, do I need you to be good at recognizing when the Pythagorean identity shows up like this, sine squared plus cosine squared, but I also need you to be good with the variations of it. So up here, we know that if we subtract sine squared, sine squared theta from both sides, then we're going to get that the cosine squared theta is 1 minus the sine squared of theta. So also be able to recognize the Pythagorean identity when it's written like that. So I can say that this 1 minus sine squared t is really just the cosine squared t. And now we can see how that cosine is going to be able to go away in our denominator. So I cancel this cosine out with one of these cosines, but I'm still left with cosine t, which is going to give me the cosine of t over 1 minus the sine of t, which is in fact my right-hand side.